Now that we've seen in multiple examples that a matrix transform that scales specific vectors or specific directions can help to understand what a whole matrix is doing. In fact, it's equivalent to knowing the whole matrix. Here we get down to how would we actually identify those transforms if someone gave us the matrix to start with. Here we're going to introduce and start using the terms eigenvalue and eigenvector, but they're exactly the concepts you saw before. What direction gets scaled? That's the characteristic vector. And what does it get scaled by? That's the characteristic value or the eigenvalue. What we saw earlier is this boils down to a simple equation. If we have a linear transform L and it transforms a particular vector to the same vector again, but scaled, so this together is a scaled version of the same V, so no direction change, just the idea of extending, flipping, or contracting. We can write that in matrix form. Instead of using the transform of the vector v, we can say the A matrix multiplied by v gives us lambda v. And remember, these vectors and values are always going to come in pairs. We saw in earlier examples where one direction got scaled by 2, but another direction got scaled by 1/2. So the lambda and the v go together, and for a different v, you might find a different lambda. And this is what we're going to call either the eigenequation or the eigenvalue-eigenvector equation if we're being thorough. So let's use that new terminology in our previous example. We had the matrix 3, 1, 0, 2, and we found these products. So this is our A times V calculations. And we noted when we put in 1, 0 as the input vector, we got 3, 0 back, but that is just 3 times 1, 0. And so the way we would say that now is, so the vector, let's call it V1, is 1, 0, is an eigenvector. It's a characteristic direction. It's an eigenvector of the matrix A. And with corresponding eigenvalue, characteristic value or scaling eigenvalue of lambda 1 equals 3, which is the same thing as saying A will scale 1, 0 by 3, and I'm going to say 1, 0 or multiples of it. Anything in the subspace defined by that, if you want to get technical. A will scale this vector by 3 is the same thing as saying this vector is an eigenvector of A with corresponding eigenvalue of 3. One of the other vectors we worked with was the other basis vector 0, 1, or the y-axis vector. When we transformed that using A, we got the vector 1, 2, and we can see right away that this is not a multiple of the 0, 1 that we started with. And so we learn right away that 0, 1 is not an eigenvector of A. It's a lovely vector, and we love the vector 0, 1. It's a great basis vector, but it just so happens for this particular transform, it's a more complicated operation when we apply A to this vector. We get something in a new direction. 1, 0 is great for this matrix and for this transform because we get a simple multiple back. And last but not least, we did see that the vector negative 1, 1 did have this characteristic again. We start with negative 1, 1, we get negative 1, 1 back except scaled by 2. And so we'd say here, so a second vector that we just found is an eigenvector of A with corresponding eigenvalue lambda 2 equals 2. Or said in another way, this matrix A will scale the vector of negative 1, 1, or any vector parallel to that, and you multiply it by 2 when we do the transformation. That's it. That's how we use the terminology of eigenvectors and eigenvalues. In the following videos, we'll see how to actually compute these. Here we kind of got lucky and guessed what the vectors would be. We'd like to have something more systematic for that, and we'll see how to build that out of the eigenvector-eigenvalue equation.